All right, so now we have a basic idea, general idea of how the periodic table was developed and how it's arranged. Now we're going to focus on our electrons again. So remember now, the electrons are subatomic particles that are found outside of the nucleus. And these, the electrons, are the subatomic particles that will dictate chemical characteristics in an atom. Okay, so they will dictate how a substance bonds or reacts with something else. So it makes sense now that if we can understand a little something about the electrons, where they are, how they are arranged, that we can then, by extension, understand how that particular substance, that atom or that molecule or that ion, how it actually behaves as well. So this is why we're going to spend a lot of time in this section talking about the electrons, how they are arranged, how they're configured, etc. Because chemical reactivity, chemical characteristics can all be boiled down to the electrons. So we're going to take a look, first of all, at something known as the electron configurations. And we're going to use some of the information we learned in the previous sections in terms of our atomic orbitals, our energy levels, subshells, shells, etc. Okay, so when we talk about an electron configuration, what we are referring to is how the electrons are distributed in the various atomic orbitals that you have in an atom. Okay, and specifically now how they are arranged in terms of their energies, how they are arranged in terms of their other characteristics as well. So as a reference, we did use hydrogen as our basis for our understanding of the atom and the electron to begin with. And as a reminder, in hydrogen, right, atomic number one is going to have one electron. So it's a single electron system. So it's the simplest system that we can possibly study. And what we find in the ground state, so the ground state, which is, again, we saw this term before, we'll abbreviate GS for now, is the lowest energy state for something. In this case, the hydrogen atom. That electron, that one electron, is located in the 1s orbital. Okay, so if we have an electron in that 1s orbital, we can show it in what's known as a orbital diagram. And we'll see some more of these down the road, where we list the orbitals in order of increasing energy. Okay, and what we'll see down here is that our lowest energy here that we have, lowest energy orbital, is the 1s orbital. Now, one important thing to keep in mind as we start dealing with these electron configurations, orbital diagrams, etc., and this is really important, a single orbital can accommodate a maximum of 2 electrons. Okay, so that's as many electrons as we can stuff into a single orbital. So when we have this one electron in hydrogen, that one electron goes into the lowest energy orbital there is, which is the 1s orbital. So we say 1s, and when we put the number of electrons in that orbital as a superscript. So this is read, the way that you would read this is as follows. You'd read as 1s1. Okay, so it's the notation, the lingo is very important. So the 1 here refers to this number. The S obviously refers to the letter, and then the 1 at the end, that refers to the superscript. Okay, so what do these actually mean in a electron configuration? Okay, so the 1 and the S and the 1. This first letter here represents the N value. the principal energy level, the principal quantum number. S here represents the angular momentum quantum number, the L value. Okay, remember L can be from has certain values, and then the superscript 1 here represents the number of electrons in that orbital. Okay, so remember now, just as a recollection of what we learned before, if n equals 1, the first energy level, L can have values from 0 to n minus 1. All right, so we'll have 0, and then obviously n, which is 1 minus 1 is 0. So the only L value possible there is 0, and L is equal to 0 corresponds to, that's the s orbital, or the s sublevel. Okay, so whenever you see your electron, we'll see several of these electron configurations. That's how we read them, and that's what the numbers mean. Now we're going to take a look at what the different types of rules that we use to establish or to write electron configurations. So if we go back to the hydrogen atom, right? So we talked about it, in the ground state, right? This is where the electron is, and in your orbital diagram, we typically represent an electron as an arrow, specifically as a half-headed arrow. In an orbital. Okay, and the orbital there would be just a simple box, which is this thing. So in the ground state, right, this is where that one electron is. We put it in as an arrow, half-headed arrow, pointing up typically. Now, if we excite that electron, we give it some energy, right, that electron can jump to a higher energy level, such as up into the 2s orbital, and then it would have an electron configuration of 2s1. So the 1s then would actually be empty in the excited state. Okay, so we wouldn't have this electron here. We can just write it in as a dotted line just to show where it was. As we get excited, as we give it some energy, heat energy, light energy, whatever, it can jump to a higher energy level. So the electron configuration then is going to change. And again, now this is for a single electron system like the hydrogen atom, which is the simplest system that we have. So we saw these emission spectra before, the fact that one electron then can be excited, it can drop back down to different energy levels, is represented in its line emission spectra. Okay, so these are our emission spectra. Where we see these discrete lines that correspond to energies of the electrons relaxing back down from a higher energy level to a lower energy level. Now, what happens if we start adding more and more electrons, so hydrogen again being the simplest case with just one electron in it, when we start going to the right and down in the periodic table, you'll notice that the majority of the elements on the periodic table have more than one electron, right? All of them have more than one electron, except hydrogen. So once you start introducing more electrons, guess what happened? Electrons have a negative charge. And if you have negative charges close to each other, they will tend to repel each other. And when that happens, it leads to something called splitting of the atomic orbitals. Okay, so typically, in the case of hydrogen, if I go back up, we can see that in our n equals 2, which is this level here, so the second energy level, the principal quantum number is 2 in this case. What are possible L values? Well, L can be 0, and then it can go all the way up to n minus 1. So what's 2 minus 1? 1. L equals 0, as we know, corresponds to the S sublevel, and L equals 1 now corresponds to the P sublevel, which is going to be this sublevel here. And if we keep, with the hierarchy of this, For our L values, okay, now we can use those to come up with our M sub L values. M sub L values go from negative L through 0 to positive L. So if L is equal to 0, right, then our M sub L only has one value, which is 0, because negative 0 is the same as 0. For L equals 1, we have our M sub L values of negative 1 through 0 to positive 1. So we have 3 of these M sub L values, and these correspond to the 3 p orbitals, right? We have 3 of them, and there they are, our first, second, and our third. Okay, in the case of the hydrogen atom, all of these orbitals, the 2s and all of the 3 2p's, they're all equivalent in energy. When we start looking at multi-electron systems, what happens is that second, third, fourth, fifth electron, there's a bunch of electrostatic interactions between multiple electrons. Okay, so in multi-electron atoms, okay, the presence of extra electrons or of more electrons causes electrostatic interactions. Okay, remember now electrons are negative. So we have negative and negative charges, they will tend to repel each other. And as a result, what happens now is that those energy levels or the energies of the atomic orbitals are now split. Okay, so we call that splitting of the energy levels. So in the case of the second energy level, so n equals 2, which is here, okay, what you will notice is that the 2s and the 2p, these are not the same energy, okay? Not equivalent in energy. The 2s is actually lower in energy than the 2p. And similarly, in the case of the n equals 3, okay, which accounts now for the 3s, the 3p, and the 3d, these are all the third energy level orbitals. You will notice now that these are not equivalent in energy either. There's a splitting of these energy levels such that now the 3s is less than the 3p, and the 3p is less than the 3d in terms of energies. Okay, so you have the splitting of the energies of the orbitals in multi-electron atoms. And that's going to be the case for 99% of the elements on the periodic table because all of them are going to have more than one electron with the exception of hydrogen. So a couple terms to note, or a couple things to note here when we start looking at our different energy levels. When you have the splitting of these energies of the atomic orbitals, you now have sort of the commingling of these energies such that, for instance, we find here that the 3d sublevel, okay, is actually higher in energy than the 4s sublevel. Okay, so these are all the n equals 3 energy levels. They're split. And they're split far enough that the 3d is actually higher in energy than the 4s. And the 4, the n equals 4 orbitals, these are also split, right? So your 4s is lower than the 4p and the 4d, and if you keep going up to the 4f. Okay, so that's very important to keep in mind because it will dictate how we start stuffing electrons into each of these different orbitals, which represent these different, which are represented by these different boxes. So a couple of things, one more thing to note about this initial treatment here of our orbital diagrams, you'll notice that all of the 2p sublevels, all the 2p orbitals, okay, all the 2p orbitals are equivalent in energy. And we call those degenerate orbitals. Okay, when they are equal in energy, that's the term that we use. So all of the 2p are degenerate. to each other. All of the 3p are degenerate to each other. All of the 3ds, all of the 4p's are degenerate to each other. All the 4ds are degenerate. And again, that makes sense because they all belong to the same subshell, which is the D in case of the 4d or the P in case of the 4p. So now what we're going to do is we're going to take a look at some of the rules that we need to follow when it comes to deciding what the electron configuration for an atom or an ion or whatever species it is that we're looking at is going to be. So the first rule that we're going to use to guide us is called the Pauli exclusion principle. And the Pauli exclusion principle is named after a scientist, Wolfgang Pauli. A lot of these are named after scientists, by the way. He was actually a physicist, won the Nobel Prize in Physics in the early 1900s. And according to his principle, no two electrons in an atom can have the same four quantum numbers. Okay, and that is going to be important because it tells us, or it's the explanation for why we can only have a maximum of 2 electrons in an orbital, and why they need to, for example, be oriented in opposite directions. So, for instance, if I have a helium atom, okay, and if you recall, helium, let me see if I can paste this on here. There we go. So helium is over here on the right side of our table. It's got 2 protons, okay, and the helium atom will also have 2 electrons. So according to what we said earlier, those 2 electrons have to go into the 1s orbital first, okay? So if I have I'll just rewrite this. This is my 1s orbital. I write it as a box. My first electron goes in as an arrow pointing up. My second electron, I'm also going to write as an arrow. Okay, it cannot be pointing up. What this pointing up means, okay, this is an idea or an indication of the electron spin. Okay, so the orientation up by default or by definition means that that spin is plus 1/2. Okay, and if you remember, the fourth quantum number is the m sub s value, right? That's a spin quantum number for an electron. And in this case, if you have an electron pointing up, we're saying that that's a spin value of plus 1/2. While the other option for that is to have a spin quantum number as negative 1/2, and that would mean that that electron then would be pointing downwards, going this way. And this is important because if we were to deduce or come up with the quantum numbers for an electron, for these electrons in the 1s orbital, if we have our first electron in there, so this one, for instance, pointing up, it's in the n equals 1, right? Principal energy level. We've seen that the L value for that, for n equals 1, is going to be 0. We've also seen that the m sub L value for that has to be 0 as well. Now, if I had another electron pointing downwards, okay, it's it is in the n equals 1 value as well. Its L value is also going to be 0, and its m sub L is also going to be 0. Okay, for this electron on the left side, okay, its spin quantum number, its m sub s is positive 1/2. The one on the right side that's pointing down, okay, that's negative 1/2. If they were both pointing upwards, okay, so if this one was pointing up and the other one was pointing up, okay, these would both be, they would both have the same set of quantum numbers, including the spin. So this would be plus 1/2, and the other one would also be plus 1/2. What we're saying is that is not allowed. Okay, according to the Pauli exclusion principle, what's also not allowed is to have both of them pointing downwards. Okay, that is all, because then they would both be negative 1/2, and they all have all the other same quantum numbers. That's not allowed either. So they have to be pointing in opposite directions. We say then that these electrons have to pair up with opposite spins in that in that orbital, right? So we have a maximum of 2 electrons in each individual orbital. They pair up with opposite spins so that they don't have all 4 quantum numbers being the same. That's the first thing that we need to figure out, or we need to follow. The second is sort of intuitive, and that's called the Aufbau principle. And according to the Aufbau principle, this is a German word, I think it's German, that means sort of building up specifically from the lowest energy first. Okay, so all this means is that if we need to configure a bunch of electrons, we're going to stick those electrons into the lowest energy level. We're going to fill those energy levels first before we move to any higher energy orbitals. Okay, so we start at the bottom of our energy diagram or orbital diagram over here, for example, and we're going to fill the 1s first. Then if we have any other electrons, then we're going to put those into the higher energy levels or higher energy orbitals, for example. Okay, so lithium, for example, has 3 electrons. So those first 2 electrons are going to go in here. So we end up with our 1s, and we have 2 electrons. Then that third electron has to go into the next energy level, which is the 2s. So that becomes then 2s1. There's 1 electron in there. We put these together. We end up then with 1s2, 2s1, right? And that's the way that we would read this. Okay, 1s2. And then 2s1. Okay, not 1s squared. 1s2, and then 2s1. That's how you would say that to somebody to report that electron configuration. Okay, so Aufbau building up. We fill the lowest energy first, lowest energy orbitals, then we put any remaining electrons into the next energy orbital, etc., until we've accounted for all of the electrons. And remember, every orbital can only accommodate a maximum of 2 electrons. Okay, and that's the case not just for the 1s orbital, but any other orbital. If we keep going on, we look at beryllium, for example. So beryllium has a total of 4 electrons. Okay, first 2 electrons go into the 1s, so we have our 1s2. The next 2 electrons will go here. So this gives us a 2s2. Put them together, we end up with 1s2, 2s2. Keep going across the periodic table. We go to boron. Boron has a total of 5 electrons. So we already talked about the 1s2 and the 2s2. The fifth electron then goes into the next energy level, which is the 2p. Okay, and just by default, because this is the first 2p orbital, remember we have 3 of the p orbitals. Okay, we always have 3 p orbitals in any any principal energy level that has p orbitals. We always have 3 p orbitals. It doesn't matter which one you put it in first, just put it in one of them first. Okay, so case of boron, those 5 electrons, 1s2, 2s2, 2p1, right? Double check. You add up your superscripts. Guess how much you should get? You should get the number of electrons that you are trying to configure. Okay, so add the superscripts to get the total number of electrons. That's a quick way to double check your answer. All right, so the next rule that we're going to follow is called Hund's rule. Okay, and a Hund's rule you can think of as an analogy to this, and when I explain this to students, I sort of refer to it as the bus seat rule. Okay, or you can think, I mean, whatever, airplane seat or train seat, whatever your favorite mode of public transportation is. And you can think about it this way, okay? So if I have carbon, for example, and I'm going to draw a new energy level orbital diagram here on the right side. This is my energy. You have my orbitals. I have my 1s, I have my 2s, and I have my 2p's. I have 3 of these. Remember, The p orbitals, they correspond to the different orientations. You have a 2px, a 2py, and a 2pz. Okay, so for carbon has 6 electrons. Okay, the first electron is going to go according to Hund's rule. Fill that lowest energy orbital first. Second electron has to pair up, again, according to the Aufbau principle, and then Pauli exclusion principle as well. So we put the second electron in, pointing in the opposite direction. This is now filled. Third electron cannot go here. It needs to go into the next higher energy level orbital, which is the 2s. So the third electron goes in. Okay, by convention, you put that one pointing up. The fourth one has to come in here to fill this one first. So we fill that with the 2 electrons and the 2s. Okay, those are 4 electrons. The fifth electron goes into one of the 2p orbitals. Okay, that's 5. We have a total of 6. Where is that 6th electron going to go? Okay, and you may be tempted to say, you know what? I'm going to put that electron here, right next to it, because I want to pair it up. And that's a very rational thing to do. However, according to Hund's rule, what we need to do is we need to actually put that electron into the next 2p orbital. We don't want to pair that up if there is space to put that electron in an orbital on its own. And the idea why I call it the bus seat rule is that if you imagine going onto a bus and you're the first person on the bus, you're going to grab a seat, right? An open seat wherever. The next person to come on the bus, when they have to pick a seat, they are probably not going to sit right next to you. They're going to pick a row that is empty and they're going to sit there. And you can think about that going on and on and on. Next person comes on, they pick a row that's empty, right? This electron, this purple one coming in, it picks a row or an orbital in this case that's empty. If I have another electron coming in, that's going to pick one that's empty. And if I have another electron coming in, guess what? Well, at this point, just like on the bus where all the rows have one person, when the next person comes in, they then have to sit next to somebody. Just like in this case, if I have another electron to configure, now I have no choice but to pair up. And when you pair it up, it has to point in the opposite direction. Okay, that's Hund's rule in a nutshell. So the way that we would say that is we put one electron in each of the 2p orbitals first before we start pairing up. And the reason why that is important is because these p orbitals are degenerate, right? They have equivalent energies. Degenerate p or 2p orbitals to be more specific. Okay, so we put one in each orbital, but then we start pairing up. So don't pair up prematurely, in other words. So let's go back to the carbon now. So we had 6 electrons that we were configuring. So let's go back here. Our electrons are in orange. So we have our 2 and the 1s, our 2 and the 2s. We have 1 in the 2px, and then another one then will want to go according to Hund's rule, want to go into the other 2p orbital. So we end up with 1s2, we have 2s2, and then we have our 2p2. Okay, we don't designate or we don't differentiate between the px, py, pz. We just list it as the subshell itself, just a 2p subshell. We have 2 electrons in there. And that's the electron configuration for carbon. Okay, so and again, the reason for that, according to Hund's rule, is stability, right? So we're looking to get the most stable arrangement of the electrons, and that is one in which the number of electrons with the same spin, in other words, by default, we're doing spin up, being in the initial spin, is maximized. So in the case of nitrogen with 7 electrons, okay, we have our 1s2, 2s2, the next 3 electrons will go into one of the p orbitals first to maximize the same spin in each of them. So we don't pair up these electrons prematurely. Okay, because what that will do is that will make it unstable if we did that. Instead, we maximize the same number or the same spin up in this case, that's more stable. Okay, and if you just keep stability in mind, it's really the answer to most questions in terms of electrons and just chemical reactions in general. Okay, and we keep going for oxygen. So now oxygen has that eighth electron that comes in. Well, that eighth electron now has no choice, according to Hund's rule now, than to start pairing up, and it pairs up with the spin down to counteract that spin up from the first of the two p orbitals. Okay, and we keep going all the way across the periodic table until we account for all of the electrons that we need to. So if we account, or if we put our electrons into our different orbitals according to the Pauli exclusion, according to the Aufbau principle, according to Hund's rule, what we will see is that there is a way in which we can organize the electrons in a way that makes sense. You can summarize them as follows. Electrons will reside in the available orbitals of lowest possible energy. Okay, so that's the Aufbau principle, building up from the bottom, the lowest energy first. We also see that each orbital can accommodate a maximum of 2 electrons. Okay, that's the Pauli exclusion principle. We've also seen that electrons will not pair in degenerate orbitals if there is an empty orbital of equivalent energy available. That's Hund's rule. Okay, so this is Hund's rule down here. We'll write the names for these. The maximum of 2 electrons, this is Pauli exclusion. And then building up from the lowest possible energy, that's Aufbau. Okay, so all of these 3 principles and rules we can put together, and we end up with an order of filling the orbitals that looks something like this up here on the right side. This is sometimes called a Christmas tree diagram of filling the orbitals, and you will notice that they are not, it's not intuitive. In other words, we don't fill all of the the n equals 4 levels first. We do them in this particular order. So for example, the way that you would read this, okay, we're going to fill, according to this, we're going to fill the 1s orbital first, the 1s sublevel. Then we go to the 2s. Then we go to the 2p. Then we go to the 3s. Then we go to the 3p. 3s, then we go to the 3p. Then we go to the 4s. If you recall from earlier on, that's because of the energy splitting. Then we go to the 3d. Then we go to the 4p. Then we go to the 5s. Then we go to the 4d, etc., etc., etc. Okay, so this, I mean, you can by all means memorize this if you want to determine the order of filling the electrons. We're going to show you how you can use actually the periodic table to come up with this same information. So if you want to commit this to memory, by all means, more power to you. Go ahead and do it. However, I will tell you that the periodic table can help you get the same information. Okay, so often you'll see in other textbooks, the arrows kind of look like this. Okay, so it kind of curls back around like so. So it gives you a much better idea of how these orbitals are being filled. I'm not going to do all of them, just to kind of show you how it goes. So the 1s first, then the 2s, and the 2p, 3s, 3p, 4s, 3d, 4p, 5s, etc., and etc.